Okay, so let's remind ourselves what we have done thus far. We have defined what is called an interaction picture, and the advantage of using the interaction picture is that the time evolution of the kits in the interaction picture depend only on the time dependent part of the Hamiltonian. In other words, we have frozen out all the time evolution of the kits because of the presence of H0. Okay, the presence of H0 of course also causes a time evolution, but that time evolution is simple and something that we already know. This is e to the minus IET over H bar. So we have basically frozen that out. Okay, and we have also made some remarks as to how this definition, interaction kit definition, is different from the Heisenberg kit definition. Okay, Heisenberg kit is basically freezing out all time dependence from the evolution of the kit. So kits don't time evolve at all. Interaction kits is basically freezing out the time evolution due to the free Hamiltonian. Okay, so that whatever you have is because of the perturbing part. All right. So, okay, so this is showing up properly. So we will begin from here, and we will need, basically, if I find out what the time evolution operator is in the interaction picture, then I'm basically done. I've solved my problem. In other words, all I'm claiming is that in the boxed equation, I can write down a formal solution. What is the formal solution? The formal solution is psi of t is some time evolution, but in the interaction picture. Okay, so this is all I need. Once I solve for this u, which we can call either the time evolution operator in the interaction picture or the propagator or whatever it is that you want. Once I solve for this u, I'm basically done. Okay, the question is how to solve for u. So remember, so basically let's plug this back in the boxed equation. So IH bar ddt of ui tt0 acting on psi of it0 equals, excuse me, h ui. Okay. So remember, on the left hand side, the ddt part acts only on the ui because psi I at time t equal to 0 is not a time dependent function. It is simply the get evaluated at the time t equal to t0. If you choose t0 as 0, then it is the kit at time t equal to 0. So since this equation is valid for an arbitrary starting kit psi I of t0, I can turn this into an equation for ui. IH bar equals h tilde. Okay. And once I know what the solution for this equation is, I'm done. The goal is to find, compute ui t0. Okay. And once I compute the time evolution in the interaction picture, I can compute the corresponding time evolution in the Schrodinger picture. How is that? See, remember the original problem that we started with was in the Schrodinger kits. Of course, these are all related by some unitary transformations. So if I can calculate ui, I should be able to calculate us. The way I would do it is by starting with the definition. So remember that psi I of t we defined by claiming that this is psi s of t, right? So basically, we threw out all the e to the minus. So psi s of t time evolves according to e to the minus IET, and the US0 dagger is basically e to the plus IET. So all the e to the IETs are thrown away. That was the point of this exercise. And we also defined psi I of time t equal to t0, the starting point, to be the same as the Schrodinger kit. Okay, this is arising from the fact that US T0 is just the identity operator. Okay, evaluates at the same time, it becomes the identity operator. Okay. So take this equation, take the first equation, and I can rewrite this guy as US t0, excuse me, psi I of t equals psi s of t. Okay. But what is psi I of t? Psi I of t I don't know. I'll just stick with this equation. Sorry, I don't need to invert this. I'll simply plug in. I'll simply plug in how psi s time evolves. So from this equation, I can write psi I of t equals us0 et0 dagger. Psi s of t, the Schrodinger cat, time evolves according to us t0 psi s of t0. Okay. So I can, since at time t equal to t0, doesn't matter if I call it s or I, they're both the same. I can rewrite this equation as us tt0 dagger us tt0 psi I of t0. Okay. So if you compare the first equation and the second equation, okay, where we have written down the time state ket psi I of t in two different fashions, starting from psi I of t0, you can clearly see that the time evolution in the interaction picture ui t t0 can be thought of as the composition us tt0 dagger us tt0. Okay, which means what, since I know us0, this is just e to the IEHT. If I can figure out UI, I know US basically. Okay, and I know the solution to my problem. So the question is, how will I set up a perturbation series for this guy? Okay, so let us again start with the fundamental equation. So IH bar ddt of UI t comma t0 is h tilde ui t comma t0. Okay. Now you might think that I can simply integrate this. Remember that the solution is not e to the minus I h tilde t minus t0 over h bar. This, even though it looks identical to the Schrodinger equation, and it is basically the identical to the Schrodinger equation, the difference being h tilde is time dependent. So I cannot simply integrate this by assuming h tilde as a constant. I can get this particular time evolution only if h tilde is a constant. Okay. So the way I would do this is by formally integrating. What is the formal solution? The formal solution I can write down. The formal solution can be written down of this equation as ui I minus I over h bar t0 to t of h I ui t prime t0 dt prime. Okay. So basically I need to motivate this form to you. First of all, are there any questions about this differential equation? So that simply follows from the Schrodinger equation set up in the interaction picture. Okay, so why is this the formal solution? Well, if I simply take this differential equation and I integrate this, you would think that I should only get the second part, right? Why do I get the I here? The I here I get because I need to respect the boundary conditions. Remember that at time t equal to t0, we define the propagator to be such that ui is identity. Okay, nothing happens. So if I put t equals t0, the integration vanishes because I'm integrating from t0 to t0. The integration part vanishes, so ui becomes I. So the first I is necessary because of the initial conditions. The second part, of course, is basically the formal solution to this differential equation. Now, the way to verify that if this is the formal solution is to basically plug this solution back in this differential equation and check, and I leave that to you as an exercise. So you can plug this formal solution back in the differential equation and check that it is indeed satisfied. Okay. But this is hardly a solution. Why is this not a solution? Well, our goal is to figure out the time evolution, UI, right? But there is no way I can solve for this UI, because if I want to solve for UI, I should write UI in terms of things that don't depend on UI, okay? But look at this equation. You have a UI on the left. In order to figure out UI, I need UI on the right. I need to know UI to figure out UI, okay? So this is not really a solution in that sense. So what we have basically set up is what is called an integral equation. Okay. So this is something that we will also do, for example, when we do scattering theory. The way to solve this integral equation is by approximating order by order. So I will first tell you how to formally do this, and then I will give you a pictorial understanding of what this actually means. Okay. So what is it that we are doing? So again, perturbation theory is nothing new to you, so you should be able to follow the logic pretty in a straightforward fashion. The way I will solve this is as follows. So I'll assume that the perturbing Hamiltonian H tilde of T prime is rather weak, okay? Which means to linear order, to zeroth order, for example, to zeroth order, what is my UI of T0? UI of T0, if I simply set all the perturbation to 0, is simply I. What does this mean physically? It simply means that if there is no perturbation, then a state that starts out as one particular eigenstate of the unperturbed Hamiltonian will stay as that particular eigenstate of the unperturbed Hamiltonian. Okay, there is no way a transition can occur simply because we have set H tilde of T prime to be 0. Okay, so this is the rather uninteresting part, and this we already knew. So the first non-trivial non-trivial result is the first order result. How will I solve the first order? To first order, I need to figure out UI to first order, okay? Which means I need to compute things to first order in the perturbation on the right hand side. Remember that the full solution, we are thinking of UI to be some kind of a series whose linear zeroth order term is I, okay? And then there is some term proportional to the action of one insertion of H tilde and something proportional to 2 insertions of H tilde, and so on and so forth, okay? So in other words, we are thinking U in terms of a perturbation, a series in the perturbation. So if we want the first order correction to the propagator, then on the right hand side, I will use the zeroth order result. I have to use a zeroth order result on the right hand side because the way this integral equation looks, there is already one H tilde out front, which means if I want to compute the right hand side to first order in H tilde, I'll have to set UI to zeroth order. If I want to compute the right hand side to second order in H tilde, then I can take the terms in a UI to order H tilde. If I want to compute the right hand side to third order in H tilde, then I should take UI to be second order on the right hand side. That will make sure that I'm computing everything to third power in H tilde, and so on and so forth. So whatever power I want to compute in, I'll have to take UI on the right hand side to be one power less. Because of this particular integral equation, there is already a factor of H tilde out front. Okay. So if I want to evaluate this to first order in UI, I will have to take the zeroth order result on the right hand side. But the zeroth order result is basically UI is just the identity, which means to first order, I can write my solution UI to be I minus I over H bar integral T0 to T H tilde of T prime dt. Is this clear? Are there any questions about this? So this is why this particular picture is very clear, because generalizing to second order and third order becomes quite straightforward. Why? Because if I want the second order solution, what should I do? Ui t0 is I minus I over h bar integral t0 to t h tilde of t prime. Now I should compute u to first order. So which means in this, the u over here, I should insert this particular u. Okay, so this is basically I minus integral t0 to t t prime h tilde, I'll use a different symbol, dt double prime, dt prime. Okay, so I'll write this out correctly. This is equal to I minus I over h bar. There is two terms here. The first term, of course, is the first order result, h tilde of t prime dt prime. And the second result is minus I over h bar plus minus I over h bar whole square t0 to t, t0 to t prime, h tilde of t prime, h tilde of t double prime, dt prime, dt double prime. Okay. So to third order, I will have another insertion of h tilde. If I want to evaluate a third order, then I will have plus minus I over h bar cubed. So what is this? Is t prime goes to t0 to t, and this is t double prime goes to t0 to t prime. I will explain the integration limits in just 1 second. So if I want to third order, I will simply have h tilde of t prime, h tilde of t double prime, and h tilde of t triple prime. Okay, and plus so on and so forth. You can clearly expand this to any order you like, but practically speaking, the first order results gives you most of the things that are of direct physical interest, and in some cases you'll have to compute the second order result. Okay, so I will explain this perturbation series in terms of a picture that might be a little more easy to understand. Okay, so first of all, think of think of this in terms of a very commonplace example, right? So let us say that you are going from one end of a long hall to the other end of the hall. Okay, so let us say that this is the hall. You're going from here to there. Okay. Now we are talking about time domain and this is space domain, but this is just to give you a rough picture of what is going on. And assume that this hall is filled with a lot of people. Okay. And assume that you don't like most of these people and those people don't like you. Which means as you move from one end of this hall to the other end of this hall, nobody is going to talk to you. You're not going to talk to nobody. So you're just going to start at this end and go to that end without being disturbed by anybody in this hall. Okay. But let us say that you have a little amount of friendship with one person. Then it is possible that as you move from one end of the hall to the other end of the hall, this one person might stop and say hello. Okay. So initially you're just going to go from this end to that end. Okay. But there is a possibility that if there is one friend that you have, then you can just talk to that friend and go. But assuming that you have two friends who are in this hall, then you can say hi to both of them at some point and then go. If there is three friends, then one, then other friend can also stop you. The third friend can also stop you and go on, so on and so forth, right? So if the room is filled with strangers, then the chances that 3 interactions and 4 interactions and 5 interactions can happen is very, very rare. At most, you're just going to zip through straight away, or you're going to be stopped once or twice. That is it. Okay. So this is the sense in which I want you to understand the perturbation. So people you don't like is simply a common way of saying that the interaction is weak. Your interaction with the people in this room is going to be weak, which is why you're not going to have a lot of camaraderie with people, right? So assume that it is, instead of random strangers, it is filled with all MSc students of IIT Gandhinagar. Okay, then there from the point 0 to point L, when you traverse this hall, you're going to spend a lot of time talking to people, socializing and things like that, right? So that is a highly interacting system. But we are thinking of a system in which the interaction is actually quite small, and which is why I can think of this as a legitimate way of understanding this in terms of a perturbation series. Okay, so what is it that I mean in this particular way of setting up the equation? This way of setting up the equation, this is pretty much everything I said also holds true, except that I'm operating in the time domain. So I have, so let us say the time goes in this direction. Okay, this is t. Now, what is it that I'm computing? I'm computing the transition probability for a state to start in some initial state, okay, and then have some kind of interaction, okay, and then so there is, so I'll write this picture in the Schrodinger picture, but you can also write this in the interaction picture, whatever that is comfortable. This is time t equal to t0, this is time t equal to t, and all this is the interaction. Let us say, basically, I'm trying to understand this time evolution. This is what I want to figure out, right? This is basically us t0. I can understand this time evolution of the probability amplitude, that the state that starts out at time t is equal to t0 might end up in a different state at time t equal to t, can be thought of as a sum of the initial configuration is there is no interaction, which means the initial configuration, the first term in this perturbation series is I. I in terms of this diagram is just a straight line, okay? That starts at t equal to t0, ends up at t equal to t, and the time evolution is basically us0, the unperturbed Hamilton. This is the first term in the perturbation series, okay? This is how I'll diagrammatically represent the first term in the perturbation series. There is no interaction, there is no talking. The system simply time evolves according to the free Hamiltonian. Okay, so far so good. So how do I write down the first order interaction? The first order interaction is basically, it starts out at time t equal to t0. Okay, starts out at time t equal to t0. Okay, it quietly keeps evolving according to the free Hamiltonian, but at some point t equals t prime, it interacts with the external perturbation. So this is term t equal to t prime. Okay, and after it interacts, it quickly recovers and then goes to the same point t by evolving with the free Hamiltonian. So there is one insertion of the interaction. Okay, so just like in the crowded room, you have one person stopping you and saying hello. Okay. Now, where does this t prime occur? I don't know. So at what time point does the system interact with the external perturbation? I cannot say this with certainty. All I can say is that this happens to first order at some time between t0 and t. Okay, so I'll have to account for this possibility that the system interacts with the external perturbation at any time between t0 and t, and that is why there's an integration between t0 and t with respect to time dt prime. Okay, so this is how you understand the first order term as a picture. How do I understand the second order term? Well, by now I think you can quickly grasp what's going on. The system starts out at time t equal to t0, evolves freely, nobody is stopping it, it is perfectly happy. Okay, and then it gets stopped once. Okay, and then it says okay, bye bye, and evolves again, okay, and then gets stopped again, okay, and then goes back up, and then, oops, excuse me, and reaches the final state, T. So between this T0 and the first interaction, it is free. Between the first interaction and the second interaction, it is again free. Between the second interaction and the final resting point, it is again free. Okay. So this first interaction, so where does this first interaction occur? Well, by definition, the first interaction should occur before the second interaction, right? So which is why the integration T double prime can only go till T prime. It cannot go till T0. Assuming that T prime is the later time, the first interaction has to occur before the second interaction. So this should be my so time is going this direction. So which way should it go? So this should be my T double prime, and this should be my T prime. Okay. The T prime can occur at any point between T0 and T, but the T double prime happens before T prime. Okay, so the way I have set it up, T double prime is the earlier time. Okay, so T double prime, the limits of T double prime should be between T0 and T prime, and the limits on T prime should be between T0 and T. Okay, and then you can set up the other terms of the perturbation series in this diagrammatic fashion in a very simple way. Okay, so this is the easy way in which you can understand this perturbation series in the time-dependent perturbation theory formulation. And this is actually superior to the earlier formulation because it gives you a very convenient way of thinking about things. Okay, but so if I'm simply going to stick to first order calculations, whether I use this picture or the earlier formula that I developed for df of t, it is immaterial. Okay, so remember that initially we said what was our initial configuration. So recall that we wrote down the time evolution as En0 t over h bar n0. Okay, and then we developed a formula for some transition to occur from some initial state configuration to some final state configuration of the unperturbed Hamiltonian because of a time dependent perturbation. And to first order, we discussed that the solution is basically minus I over h bar. D of t is basically the probability amplitude for a state n0 to evolve to some state psi of t, right? So this is basically some t0 to t. What is this? This was f0 h tilde of t I0 e to the I omega fi t. So let us call this some t prime dt prime. So to first order, this formula for df of t and this formula for u are exactly equivalent. I wanted to prove it, but I'm running out of time. I want to talk about something else, but this can be very easily shown. Okay, so at this point, I want to talk about one particular example of h tilde of t prime, where this formula can be used, and we can try to understand what the implications of this formula are. But before I do that, I'll stop and ask if there is any questions about any of this. Any questions or any comments? So by the way, toward the end of this lecture, please don't run away. I want to talk to you guys about the midterm exam. Okay, whoever is there. Any questions? Should I move on? Okay, so assuming that it is at least some of you are there, let us discuss a very important example. And this example has to do with what are called periodic perturbations. Okay. By periodic perturbations, I simply mean that h tilde of t can be thought of as some part that is time independent. Okay. And all the time dependence comes from some periodic uh, function, e to the I omega t. Of course, I can choose any periodic function. E to the I omega t is the simplest function to choose because any other periodic function can be expressed as some linear combinations of the e to the I omega t. So I might as well choose this. Okay. So let us simply apply this formula df of t and compute the rate of transition from some initial state to some final state because of this periodic perturbation. Okay. And this will have a lot of applications. For example, when we are talking about the interaction of atoms with external radiation and things like that, which we will discuss after the mid-semester examination. So what is the probability amplitude for some initial state to go to some final state? Because of this particular perturbation, this is minus I over h bar t0 to t. Now I don't know what h tilde of t is, so I'll keep this matrix element as such. Remember that when I write df, I'm always in the Schrodinger picture. So I don't want to put the s here because this is all in the Schrodinger picture. It is understood. This is h tilde I0. Okay. There is a e to the I omega fi minus omega t prime dt prime. Okay, the e to the I omega fi comes from the formula for df, and the e to the minus I omega t is basically the external perturbation. Okay, and this is a simple enough integral, so I'll also make it simpler by starting at time t0 equal to 0. There is no loss of generality because I can always set t0 equal to 0 and start at that particular time. This is, I don't have to do this. This is simply for ease of integration. That is all. So this matrix element is time independent. So I can pull this out. Okay. And this integration is very easily done. This is e to the I divided by evaluated between the limits t and 0, right? So this basically gives me the I cancels minus 1 over h bar f0 h tilde I0 e to the I omega fi minus omega t minus 1 divided by this, where remember omega fi is omega f minus omega I, which is ef minus ei over h bar. Any questions about any of this? Any questions, any comments? So the probability that the initial state can go to the final state is basically the mod square of the probability amplitude. So the probability can be written as this matrix element square divided by h bar square times 1 over omega fi minus omega square times mod of remember that this probability is time dependent. Okay, since we are dealing with time dependent perturbations, the probability for the system to evolve to a particular final state will be different at different times, of course. Okay. So this, you should evaluate this carefully because we cannot simply multiply by e to the minus I omega t. You should write this as real and imaginary parts and write this. So e to the I theta minus 1 mod square is basically mod of cosine theta minus 1 plus I sine theta, right? So if we calculate the absolute square of this complex quantity, you will get 4 sine square theta over 2. Okay, verify this. This is a trivial calculation which you can easily do. So the probability to go to a particular final state is now given by sorry, I should put an h bar square here, right? Because I'm squaring this. Uh, 4 sine square omega fi minus omega fi minus omega t over 2 divided by omega fi minus omega whole square. Okay. Any questions or any comments about this?
Sir, when omega phi is equal to omega, the probability is
We'll
0.
talk about this. That's a good question. We will talk about this in just a second. So before I do that, let me actually do some kind of a modification here. So this is, I'll take the 4 outside, h bar square. Okay. Actually, I'll write it in this particular way. I'll write this as sine square omega fi minus omega t over 2 divided by omega fi minus omega t over 2 square. Okay. Basically, the 4 I have written as 1 over 4 in the denominator. Okay. So basically the argument of the sign is the same as the denominator, except the denominator is squared. Okay. So I'll also do one modification. I'll multiply and divide by pi, and I'll multiply and divide by t, the time. Okay. The reason I multiply and divide by time is because I want the rate at which this transition happens. In other words, I want the probability per unit time. The probability per unit time that the initial state goes to the final state is basically the rate at which this transition happens. The rate of transition equals probability divided by time, and this rate of transition is now given by pi mod square of this matrix element divided by h bar square times sine square divided by, okay. Now let us actually try to understand what this rate looks like. First of all, if you plot this function sine square omega fi minus omega divided by 2 divided by omega fi minus omega over 2, the plot of sine square x divided by x square, if you take your favorite plotting software and plot it, you will get something like this. It will peak at x is equal to 0, and then it will oscillate, then quickly die down. Okay, so this is the function. This is the function sine square x over x square, and the peak happens at x is equal to 0. So in other words, if I plot this function sine square omega fi minus omega over 2 as a function of omega fi minus omega, okay, not as a function of time, as a function of frequency, then the maximum of this frequency, the maximum of this function occurs at, so the maximum occurs, oops, at omega fi equals omega. In other words, the maximum of this, the rate is maximal at the point where the difference between the final and the initial frequencies is exactly equal to the frequency of the perturbing Hamiltonian. Okay, so this you recognize as a condition for resonance. So there is, suppose if I want to decouple time completely. Okay, in other words, at small times, the function, so when time is very, very small or time is very, very large, this function behaves rather differently. Okay, the functional dependence of this on large times is actually quite interesting. In other words, if I wait for a long time, how does this rate look like? Suppose if I wait for a very, very long time, in other words, if I take time t goes to infinity, how does this rate look like? This is equal to pi f0 h tilde I0 mod square divided by h bar square times limit t goes to infinity of, sorry, I forgot a factor of t here. So there is a t here. I've divided by t, so the t in the numerator here is pushed over to the left hand side. The t in the denominator stays. So this is limit t goes to infinity sine square omega f(phi) minus omega t over 2 divided by pi omega f(phi) minus omega over 2 whole square t. Okay. It turns out that this is actually a representation of the delta function. In other words, limit a goes to infinity sine square ax divided by pi ax square is nothing but delta of x. Okay. So remember, the delta function can be thought of as a limiting case of many ordinary analytic functions, right? So one way you can think of a delta function is basically take a rectangular pulse and compress the rectangular pulse, right? If you keep compressing the rectangular pulse, you're going to get an infinitely high rectangle at the origin. The other way to do this is to take the sine square x over x and take the limit x goes to 0. And as you keep compressing this waveform, you're going to get an infinite peak at x is equal to 0. This is another way you can realize the delta function. You can think of it as the a goes to infinity of limit of the function sine square ax over pi ax square. This is a perfectly well-behaved analytic function, which in the limit a goes to infinity gives you the Dirac delta function. In other words, if I wait long enough, then the rate to go from some initial state to some final state is given by pi times f0 h tilde I0 mod square divided by h bar square times the delta function in the argument. So the a here my a, if I want to make a connection, a is basically omega f(phi) minus omega over 2, right? Pi. Sorry, not a, the x. And a is basically t. So if I wait, time t goes to infinity of this is basically a delta function in omega f(phi) minus omega over 2. Okay, but as you guys very well know, delta of c times x is basically 1 over mod c delta of x. So if I use that formula, my rate to go from initial to final is given by the 2 goes over to the numerator. So 2 pi f0 h tilde I0 whole square divided by h bar square times delta of omega f minus omega I minus omega. Or if I want to write it in terms of energy, I can write omega f as EF over h bar, omega I is EI over h bar. Then I can pull out a factor of h bar, which will cancel one factor of h bar in the denominator. So I can write this as 2 pi f0 h tilde I0 mod square divided by h bar delta EF minus EI minus h bar omega. Okay, and this is a very famous and very important formula, and it goes by the name of, does anyone know? It's called Fermi's golden rule. It was very, very important in the early days where people were calculating atomic transitions from electromagnetic radiation. Okay, we will take this as a starting point for our discussions post midsem, where I will discuss the interaction of atoms with radiation. Okay, so this is actually a very important and interesting topic, wherein we will think of external electromagnetic radiation as both in the classical sense and the quantum mechanical sense, and we will see how to understand the difference. So you can actually guess some of the aspects of what's happening already, right? So if I switch on an external perturbation and if I wait long enough, then if I start out at some initial state I, then Fermi's golden rule is basically saying that the chance that you will go into some final state is very high, where the energy difference between the final and the initial state is exactly equal to the energy of the electromagnetic pulse that is hitting the system. Okay, so in other words, so suppose, so in this case, EF minus EI has to be equal to H bar over H bar omega, right? EF minus EI is H bar omega. Okay, so basically all I'm saying is that my energy levels are such that the system is in some energy state EI. Okay, then the external pulse hits this and causes a transition from EI to a higher excited state EF. Okay, and such that the difference between these guys is H bar omega, which is exactly the energy of the incoming radiation. Okay, so this is basically what's happening here is basically the system absorbs energy from the incoming beam and gets excited to a higher excited state. So this is absorption. Okay, now I could have done the exact same calculation, and if I had started out, instead of saying e to the minus I omega t, suppose if I had started out saying e to the plus I omega t. Okay, then if h tilde of t were h tilde e to the I omega t, then I would have calculated the rate to go from I to f as 2 pi. Everything would have stayed the same, and except this delta function would have been EF minus EI plus H bar omega. What does this mean? This delta function is only non-zero if EF minus EI plus H bar omega is 0, which tells me that EF is EI minus H bar omega, which means the final state energy is less than the initial state energy. How do I understand this process? Well, again, if I draw two energy levels, in this case, the final state energy is at a lower state than the initial state energy, which means the atom or the system starts out at an excited state, and the effect of the perturbation is such that it de-excites the system from a higher and excited state to a lower excited state. Okay. Okay, so this is called stimulated emission. The perturbation stimulates it, and the system de-excites from a higher state to a lower state. There is something else called spontaneous emission, which I simply cannot explain using the methodology described thus far. So we'll understand what this means post-midsem when we will talk about Einstein's A and B coefficients in detail. Okay. So at this point, I will stop. And then if there's any questions, please ask.